Hello, my name is Mohammad Ibrahimpour and I'm a PhD student at University of California in Merced. Today I'm going to present our paper called End-to-End Auditory Object Recognition via Inception Nucleus. This paper has been accepted to the ICASSP 2020 conference, and due to coronavirus pandemic, I'm presenting this paper virtually using this media. That was a joint work between University of California in Merced and Accenture Labs. So first, let me define what is auditory object recognition. Basically, auditory object recognition is a process which we want to assign labels to sounds based on their characteristics. Some of the categories of interest here are sirens, dog barking, drilling, engine idling, and gunshots. So in traditional auditory object recognition pipeline, we have the raw audio files, and then we are trying to extract some features out of those files. And then after extracting the features, we can pass them to the classifiers. In this example, we have the raw audio files, and then we are extracting MFCC features. MFCC features, they're going to be male frequency capsular coefficients. And as you can see in the image, the x-axis is time, y-axis is frequency, and the colors in this image that we can see, they represent the energy of the signal. After extracting these features, we can apply either linear or nonlinear classifiers on top of these features. Bear in mind that here we are not learning features, we are just extracting features out of the raw audio files. So in this paper, we are making two main contributions. First, we want to learn features. By removing the hand engineering features, we are going to learn more specific ones. And then we are going to reduce the number of parameters while we are maintaining while we are improving the performance. Bear in mind that these two contributions, they are really important for both real-time edge computing applications and for advancing deep learning models for sound classification techniques. So what's wrong with the traditional auditory object recognition models? Basically, the traditional models, they're in need of substantial hand engineering feature extraction. And those engineered features, they need to be tuned for every single problem. And engineered features, they're not going to be necessarily the optimal features that we want to use. So what's our solution here? Well, we want to say we can actually learn features and labels simultaneously. Because why we are saying that is because deep neural networks, they have repeatedly proven that they are very effective in feature learning, and deep neural networks, they can map raw input to labels with nested transformation functions. If we are able to do that, what's going to be the advantages of this approach? Basically, the advantages are this approach is going to eliminate completely the need for feature engineering. This method is going to be able to obtain more accurate results due to learning more specific features. And then this approach is going to be more suitable for real-time applications. This is the network architecture that we are proposing here. As you can see, the network consists with 1D convolutions, 2D convolutions, inception blocks, global average pooling, and softmax. So I'm going to explain every single part of this network in the following slides to make it more clear. So we are reading the audios with 8 kilohertz sampling rate, and then on top of that, we are going to apply 1D convolution. The 1D convolution that we are applying here, it has a really good feature, which is basically the 1D convolution is going to be time position invariant, and this is exactly the thing that we want. So we can apply 1D convolution on top of the input signal in order to extract features. Right after the 1D convolution, we can have our inception nucleus. In our inception nucleus, the inception nucleus actually is built with the number of 1D convolutions that they stacked on top of each other. Basically, each of those 1D convolutions, they are having different filter sizes, and they can capture richer features. And since we need to have just one receptive field, at the end of this process, we are gonna concatenate the receptive field that came out of the different 1D convolutions in order to make just one receptive field. Look at this example here. So in this example, the previous layer is going to be the receptive field from the previous 1D convolution. So right after that, we are passing this information passing the receptive field from the previous 1D convolution to bunch of different 1D convolutions. And in this example, we have 3 different 1D convolution, and the kernel size for them are like as follows. The very first one, it has the kernel size of 4 and a stride of 4. The next one has kernel size of 8, stride of 4, and then this one has kernel size of 16 and then stride of 4. And these numbers, the 32 numbers, it's going to be the number of filters that we have. And as you can see, we have a couple of 1D convolutions stacked on top of each other in order to capture richer features. And then right at the end of this process, we are going to concatenate those filters in order to make just one receptive field. So right after the inception nucleus layer, we are going to have our transpose layer. Basically, with the transpose layer, we are trying to exchange the rows with columns in order to make a 2D tensor. If you're able to make 2D tensor, the results is going to look like as a grayscale image, which is great, because right after that we can apply 2D convolutions. So here M represents the receptive field size. N is going to be the number of kernels that we have, and 1 here represents the 1D 1D convolution that we had here. So by doing this transposition, we are going to end up with a tensor that's going to be in 2D, and it can look like as a grayscale image. So by this technique, we can actually have a 2D tensor, and we can apply 2D convolution layer on top of that. So our experiments, along with the other researchers in the literature, they suggest that 2D convolutions, they're going to capture stronger features. So that's why we are applying 2D convolutions. And our 2D convolutions, we got that from the VGG in computer vision models, which basically the kernel size is fixed to 3 by 3, and then the stride is fixed to 1. So each convolutional layer, they're going to be followed by a max pooling layer, and the kernel size for the max pooling layer is fixed to 2 by 2, and then the stride is 2. So after applying a bunch of 2D convolutions and max pooling, we are going to apply a global average pooling layer. Basically, we borrowed this concept of global average pooling from the computer vision literature as well. In the global average pooling layer, we are basically trying to aggregate the spatial activations in the very last convolutional layer. Imagine that if in the last convolutional layer we have a rectangle by the size of m by n, and then we have k of them, all we are going to do here is we are trying to take the average in the spatial locations of m by n rectangles, and then we are going to end up with k different numbers. K here, however, basically is representing the number of classes here. So we are going to end up with number of classes neurons, and by that we are going to reduce the number of parameters dramatically, and it can be considered as a regularization factor, and it may help the generalization as well. Again, this is going to be the architecture that we are proposing here. So I walked you through the input layer that we basically having a time domain signal, and we are applying a bunch of 1D convolution, just one 1D convolution, and then a bunch of 1D convolution that they packed in the inception nucleus, and then we passed it to transpose layer and 2D convolutions and global average pooling and softmax. Bear in mind that all the connecting weights here, they are connected to each other, so everything can be learned end to end with deep learning techniques here. So in our experiments, we try to run experiments on a variety of different architectures in order to capture the sensitivity of our network with different parameters. For example, we wanted to know how much our network is sensitive to the filter size. We wanted to know how much our network is sensitive to having multiple inception nucleus blocks. We wanted to know how much our network is sensitive to batch normalization. So we try to have a bunch of different network architecture in order to understand the sensitivity of our network. So for the interest of time, I'm not going to go to detail in order to understand and to explain all of those architectures, but the details of that architecture is is written in the paper, and please refer to the paper for that. So we evaluate our model on urban sound classification dataset. This dataset contains 8,000 samples, 8,000 audio files, and the length of those audio files, they are 4 seconds or less. And when we are dealing with samples that they are not 4 seconds, we are basically padding zeros to make them look like 4 seconds. And then the number of classes in that dataset is fixed to 10. Some of the classes in that dataset, they are like air conditioning, children playing, jackhammer, street music, car horn, etc. So we evaluate our model, our proposed Inception model, with the state-of-the-art approach. And as you can see here, our model is at the bottom of this table. And look at the accuracies that we got on the test set. So the accuracies that we have, it's clearly obvious that it works favorably against the state-of-the-art approach, often by a large margin. And look at the number of parameters that we have. The order of the parameters of in our networks, they are in order of thousands. For example, this one has 289,000 parameters, but the order of parameters in the other approach, they're in the order of millions. For example, this one has 129 million parameters. So one of the conclusions in this paper is perhaps having a very deep neural network is not going to help us to generalize well. And one of the reasons is because the data is limited here. So we are going to overfit right away. So since our network works well, we want to know why it's working well. So that's why we try to have some representation analysis. So in the shallow layers, we try to see what is the thing that the network is learning, and we try to plot them. And so in the very first layer, we notice that the network is learning wavelet-like features, and as we can see, the wavelet-like features that we are learning, they're going to capture different frequencies. So in the computer vision literature, we know that in the very first layer, we are learning color patches, we are learning gavel-like filters. But here, we are not learning any of those. We are learning wavelet-like features. And this is exactly the thing that we want. And we don't expect the network to learn color patches or gavel-like filters, which is a really good sign. And then we didn't stop at the shallow layers. We wanted to know what is the kind of thing that the network is learning in higher level representations. And our experiments actually suggest that in high level representations, we are learning some perceptually meaningful representations, and they're relatively separable, even in low dimensional space. So here is a t-SNE plot of plot of the representation of the very last convolutional layer, and different colors, they represent different classes. And as you can see, even in 2 dimensions, we are going to be able to separate classes fairly well. Takeaways from this research, we can conclude that using Inception Nucleus will help us to learn richer features. Having global average pooling is going to reduce the number of parameters, and it's going to increase the generalization. So bear in mind that most of the parameters in deep neural network, they happen to be at the end of the network when we have dense layers. So if we use the technique of global average pooling, we can actually reduce the number of parameters instead of increasing the number of parameters. And in these experiments, we noticed that reducing the number of parameters actually helped us a lot to increase the generalization. And then, given the relatively small data set that we have here, very deep neural network, they don't generalize well. And batch normalization in our experiments didn't help the generalization either. So we noticed that end-to-end auditory object recognition is going to boost the performance due to learning more specific features here. And our representation analysis suggests that the shallow layers in our neural network, they're learning wavelet-like features, and deeper layers in our network, they're learning perceptually meaningful representations. And smaller number of data sets, a smaller number of parameters in this technique may be actually very useful for networks that they are running on mobiles or on edge devices. So the code for this research is freely available in my GitHub page, and the link for accessing the code is appearing here. So you may scan the following barcode, and this barcode is going to receive the link for you. By that, I can conclude the talk, and we can jump to the questions. Thank you.